Thank you, Emmy.
Perfect. Okay, thanks again. So let me just quickly recap what we did in the last two lectures. We considered this hybrid kind of black hole where inside this strip, if you ignore these two wings, we had an eternal black hole in ADS2. So the metric here is ADS2. And we joined it to two external bath systems, which are flat space CFTs. I should have said that the theory here is JT gravity coupled to conformal matter. Okay? So there's a CFT living in the bulk. That's different from the CFT on the boundary. Okay? And over here and here we have two CFTs that are on flat space. Okay? So it's the same CFT everywhere, but here it's on ADS2 and here it's on flat space. The point is that, so here the ADS2 boundary, I draw it as a dotted line to indicate that, that for the bulk matter, there are transparent boundary conditions. So the stress energy of the matter here can flow through the boundary and go there, and whatever stress energy here falls inside. But the metric still has Dirichlet conditions. So it's still asymptotically ADS2 in this region. It means ADS2 everywhere. Okay, so this is the model in which we're studying the information paradox.
So say that again. And so there's a boundary. So it's a discontinuous, the cosmological constant comes discontinuous?
Yes, except that here gravity is dynamical. So there's JT gravity. Here gravity is not dynamical. Yes. Good. And I argue that one should think of this system as you can sort of consider the left and right baths. You should call that the radiation. This is just terminology. I'm calling that the radiation. And the left-right system. Actually no. But before I do this, I'm going to imagine that this bulk theory, it's an ADS, two-dimensional ADS theory, that it has a holographic dual, okay, in terms of this L and right system. So this is sort of an alternative perspective you can take for this spacetime, okay? And here you can think of this CFT as interacting with some 0 + 1 dimensional system, like SYK or something or whatever. And then, thinking about it here, one should think of the left-right system as, in some sense, the black hole, and the BL-BR system as, in some sense, the radiation. Okay?
We shouldn't take too seriously. It doesn't correspond to the division on the left. I don't understand, because this is the key equation.
I don't understand what you mean by the division on the left.
So there's a left diagram and the right diagram.
Yes.
The left diagram has a black hole in some other region.
Yes.
But it will presumably not be the case at the end that L union R will describe the middle and B union PR will describe the middle.
That's right, but that's so you're just having issue of what I mean here by black hole. But the equality of this spacetime and this spacetime, it's like a good model. But it's a model nevertheless. I'm just saying that this spacetime here can be replaced by LR, but that's not the same statement as saying that the entire spacetime here is described by LR. Okay, but we'll get to this later. Okay, the thing we did last time, or another thing we did last time, was we computed the entropy of the left and right baths as a function of time. And I showed that this spacetime, which is really just, it's a toy model for the eternal black hole, has an information loss paradox. And the paradox is as follows. So consider the two intervals like that, and compute the entropy as a function of time, but not the boost time, the time translation that breaks the boost symmetry, where you evolve on both sides to the future. Okay? And I claimed that if you compute the entropy as a function of time of left-right, you simply get an answer, you get a linearly growing piece, or entropy, for all time. The entropy just keeps going up. And there's a very simple schematic argument for this, which is that there's Hawking radiation coming out of this black hole, right? So you have Hawking modes that do something like this. This guy is entangled with this guy, for example. And also the same thing on the other side. So as a function of time, this slice keeps capturing more and more Hawking modes that are entangled with interior Hawking modes. And that's why the entropy keeps growing with time. This process is constant for all time. The mass of the black hole is fixed, and so the rate of entropy growth is dictated by the temperature, which is fixed. And so you expect a linear growth. In fact, this thing goes as T temperature times time times the central charge of the field theory. Okay, so this is what we saw last time. And why is this an information paradox? Because this says that the bath systems are, the entanglement entropy between the bath systems and the left-right systems grows arbitrarily large in time, but notice that the mass or the energy of the left-right system is constant in time. Therefore, because it's constant in time, you can assign to it a constant coarse-grained entropy. This is the coarse-grained entropy of the left-right system, which should be thought of as the Bekenstein-Hawking entropy of the black hole. Okay? So again, so I'm adopting sort of the naive picture for the moment, that the black hole, or the wormhole in this case, is dual to the left-right system. I can.
So now on the right-hand diagram, so if you do this in the right-hand diagram, there's a BL and a PR, and now I'm confused about how it's happening. So we'll just draw slices.
So you're confused about what happens?
Now we have a completely well-defined quantum mechanical system.
Then there's no paradox.
So I'm just trying to understand on the right-hand side.
Yes.
If you take L and R and you draw these same slices.
Yes. There's no, I mean.
So we have BL, so just to understand the initial state, BL is entangled with L and PR is entangled with R. Is that?
Well, no, I mean, everything's entangled with everything. It's not clear. I really think this is the distraction for now. I'm trying to review everything for Dash.
No, I understand, but I'm just trying to understand this is a question about what the answer would be on the right hand side. If you put a slice, for example,
yeah.
A full slice on the right diagram.
A right diagram, like this?
That's right.
Yes?
What is the phenomenon entropy of that blue slice?
That's really something that we're going to get to later. Because it's ultimately it's going to. Let me consider a future time slice.
Yes.
The answer is not going to be this. But the interesting thing is to see why it's not that. But that's going to come later.
So when you said S, the coarse-grained entropy is Bekenstein. This is like at the initial one before. I mean, because the black hole is evaporating. So
no. So this black hole has fixed mass. It's an eternal black hole. The Bekenstein-Hawking entropy is just the area of the horizon, which is constant for all time. Said differently, here I have some boundary nearly conformal field theories at some given energy, and So it's at some given energy, and there's a finite number of states below that energy.
just the canonical.
For the canonical entropy, for example. And that's going to be constant in time. So now we have a paradox, which is that it seems like the entanglement entropy exceeds the coarse-grained entropy. In some sense, the left-right system or the black hole has been overfilled. Okay, so we often state the information paradox as saying the black hole goes from a pure state to the mixed state of the Hawking radiation. This evolution from pure to mixed is paradoxical, but. There's an information paradox already at the page, or just after the page time. You don't need to wait until the entire thing evaporates away, which is that it seems like the entanglement entropy between the radiation and the black hole is larger than the coarse-grained entropy of the black hole. So it seems like the amount of entanglement is larger than what the black hole has room for. That's what I'm calling the overfilling paradox, which is really just the information paradox. And that's what we see here. The black hole does not evaporate away, but the entanglement between the bath and LR, or the black hole, keeps increasing arbitrarily large in this fashion. Okay, so that was the entropy of, when we computed the entropy of BLBR. But now we expect that there should be some resolution, which gives us a page curve, which looks something like this. At the beginning, it follows the growth of the entropy a la Hawking. But then once you run out of room, the page curve will simply follow the coarse grained entropy. So it's going to be growing and then become constant. The goal is to compute SBLBR that gives this answer, and also compute the entropy of LR and show that we get this answer, and show that they're the same, and they coincide with the page curve, as I just said. That's what we want to show. And the claim is if you do this, you've resolved the information paradox in this setting. Okay. So we computed the entropy of LR and we got the wrong answer. So we'll fix that later. For now, let's talk about computing the entropy of LR.
Okay? So is the statement then that you start sort of purifying the state already at that turning point?
Exactly.
So that's when the purification begins.
Exactly. Okay, so now let's compute the entropy of LR. There's a naive guess, which is to say, well, it's simply the, something you can do is you can say, well, maybe it's just I'll draw here. It's just the entropy of a slice that cuts through the entire bulk and ends on the two boundaries. So one guess is that SLR is equal to the bulk entanglement entropy of the surface LR. Okay? And it's the same thing for all time. Just keep going. But this can't be right, because the bulk entropy of LR, so if you're working, let's say, in a semi-classical approximation, we know that that the quantum state of the fields on this entire slice is pure. So the entropy of LR here, this region, is equal to the entropy of the bath. And similarly for all time. So then this thing will just give you SBLBR, and you'll get an entropy that grows arbitrarily large for all time. Okay? So this reproduces this wrong answer. Good? Okay. But then there's a more refined proposal for computing the entropy of LR, which is to use holographic entropy. Let me review what that proposal is in general. It says, given a boundary region, for any boundary region R, subregion R, you're supposed to compute the following quantity. You're supposed to consider what is called the generalized entropy, here we're working in an H-bar expansion. To first non-trivial, to first subleading order in H-bar, the generalized entropy can be thought of as the area of some surface X plus the bulk entropy of the subregion bounded by X and R. Okay? X here should be taken as a surface homologous to R, and so on and so forth. Now, this functional is called the generalized entropy. To compute the entropy of R, you first need to extremize this generalized entropy. So now you have a list of X's of what is called quantum extremal surfaces. So when you extremize R or S-gen, I guess, you get these quantum extremal surfaces. But you might have many of them. And if you do, then you're supposed to take the one with minimal generalized entropy. Okay? So this is the holographic entropy proposal. Yes?
So I have a question about this, something I never understood. So let's say you take, this works in all dimensions. So let's say you take a pure state black hole.
Yeah.
And you take R to be the full region of the boundary.
Yeah, then you get zero.
So it's zero. But so if you're going to take S bar to be the semi-classical approach, so presumably the entanglement wedge is a full slice.
Yeah.
So that S bulk is not zero.
Oh, it's zero.
Because it's a semi-classical entropy. That's some thermal thing.
No. By semi-classical entropy, no. I literally mean, so you have some space-time like this. There's some quantum state of the fields on some slice. The entropy of that is zero.
But the fields are entangled with some other fine-grained degrees of field, right?
No. When you're working the semi-classical approximation, the fields, all the fields in the semi-classical description are entangled with themselves. They're not entangled with anything else. You in this approximation, you have like a fixed background and a pure state of the quantum fields on that background. That's how you should think about it. And we'll see here some examples of that. Okay, this is the proposal.
So the metric is not fluctuating here at all.
So good. So you're doing an H-bar expansion, so you're working about some saddle. Okay, so there is a piece that's not fluctuating, but you have other fluctuations. The other fluctuations, presumably, should be included here. So they do contribute to S bulk. But there's a long confusion about how to compute entropy for gravitons and so on, which thankfully for us, it doesn't come in, because we're doing 1 + 1 dimensions, there are no gravitons.
So area of X actually does not depend upon Gn at all on the coupling cost.
To leading order does not.
What is that? So you're saying that A of X also has an expansion. And what is the meaning of all this?
Yeah, that's, so.
What is the systematics of it? That's all I can say.
There have been attempts in trying to define this in an H-bar expansion, okay? And just for the sake of time, I don't think that's relevant for us, for the application of this in the case that I'm considering. Okay, I want to consider just up to this order. Okay? So yeah, so the fluctuations of the area are not going to be important for me. Okay.
One more question. Even the fact that you get the area itself, for the pure state, is it understood if you just take the pure state, why the area is 0?
Well, if you give me a generic pure state, then I'm not sure this formula actually applies. So generic pure state, I don't know if it's actually given by semi-classical geometry.
The generic pure state, let's say, I mean, you expect the generic pure state from outside is given by semi-classical.
Yeah, but you need. Yeah, no, I completely agree with those words. But this is applying this formula. This is a formula that's applied globally, right? You need to be able to search for surfaces everywhere in the space-time and so on. So if your space-time doesn't have, there's a region that I'm not sure if I can describe it by semi-classical geometry, then I don't know how to actually apply this formula.
You can't describe it by semi-classical geometry everywhere. Maybe what you're worried about is that it was formed like exponentially far in the past or something. That's true.
Oh, you're thinking about that. I mean.
I just took a generic pure state and it's presumably described by the same semi-classical geometry. I mean, this is exponentially close to the
I'm not sure actually. So if you give me a generic pure state, I'm not sure if there's actually a picture where that generic pure state is formed from collapse arbitrarily far in the past.
All correlation functions are exponentially close to the microton.
I agree, but we don't have any precise statement about what the entire bulk spacetime looks like behind the horizon. Maybe near the horizon and so on, and on the just behind, but sort of arbitrarily far in and so on. Still not entirely clear.
You're saying we don't understand how to apply this formula.
Of course, that's what I'm saying. Okay, let's take some examples. So let's apply this formula to computing the entropy of the right boundary in the two-dimensional thermophile double state. Okay. So now there are no baths. Okay, so there's just an eternal black hole in ADS2. So in 2 dimensions, the entropy, the generalized entropy, is given by the area, which in this case is the dilaton divided by 4 G Newton, plus at some location x, plus the bulk entanglement entropy of the subregion sigma Rx. And the idea is you're supposed to move this x around until you extremize this functional. And you'll find that the surface that extremizes it is the bifurcate horizon. Okay, so this is the bifurcate horizon. Okay. So it sort of gives you what you expect.
So you're doing a little bit different from what you said on the left-hand side. So
Why?
You take 2 terms and then extremize x. You extremize the first term now.
No, I extremize both.
Why? How?
I extremize.
How did you extremize this fellow?
How did I extremize this fellow?
I mean,
Yeah, I'll tell you. Yeah, I'm getting there. So we know what S bulk is. It's the entanglement entropy of the bulk fields on this slice. We know what that formula is.
Yes.
And we also know, we know what the solution for phi. Extremize both. the sum of both. It just turns out that in this case, it's actually very special that each of them extremizes separately.
So
Exactly.
it turns out that in this
Exactly.
case it works.
In this case, it works that you can extremize both. Said differently, the classical extremal surface coincides with the quantum extremal surface. That's in this case, the ADS2 eternal black hole. That's not true in our case. So let's consider our case. So here there are many options, but before going to the options, I want to address what Spenta was asking about. So here we have it's the geometry is also the eternal black hole geometry. The dilaton profile here is identical to the dilaton profile here. There exists a single classical extremal surface in this spacetime, and that's the bifurcate horizon. Okay, that's a classical extremal surface. Good. Okay. Let me see. But that point is not going to make an appearance in what I'm going to say right now. Although I might come back to that later. Okay. So now we want to compute. We want to apply this formula to the union of the left-right boundaries. Okay. And now there are two classes of possible quantum extremal surfaces. One is what is called the trivial surface. Why I'm calling it trivial will be clear in a moment. So here, this is a case where the entropy is the entire bulk slice connecting left and right. Trivial means that there's no dilaton contribution. There's no area piece. Okay, the trivial surface is the entire bulk. Okay? So that's one option. The other option is what is called the disconnected surface, where from each boundary, so you have these two, let me see, yeah, these two surfaces, which I guess in this case are just points. It's just where the dilaton is evaluated. So phi L plus phi R divided by 4G Newton, plus the bulk entanglement entropy of the union of sigma left plus sigma right, right? So I'm literally just applying this formula. This region here, the union of sigma left, sigma right, is the bulk region that is bounded by the location of the surface X and the boundary region that I'm computing the entropy of. Okay? So
The first one is what you said earlier.
exactly.
That's not the right one in some sense.
We'll get to that. But we see we have two options. Okay. Very good. And as Rajesh just pointed out, the point here is that this other disconnected surface we had not seen previously. We missed it somehow. Okay. Okay, so now you're supposed to find, so the trivial surface, so the thing you're supposed to extremize over is the location of X. The trivial surface has no X. So the trivial surface is automatically extremal, or quantum extremal. But this guy we need to extremize, the locations of X. And now the problem is, wait.
Trivial surface just gives you the zero.
Not in this case.
It gives you this guys.
Exactly. Okay, let me.
The other one you're saying it's not extremized by the sum of the sort of the extrema. It's not like when you put XL and XR both bifurcated. The second one.
The second one. Yeah, exactly. It's not because of this.
Because that there's an entanglement contribution.
I said something which is a bit incorrect. It's not just because of this. The quantum state in this region is different than what the quantum state was in this region. Because there's this other, because it's coupled to the bath. The quantum state is different, and that's really why we get different answers.
How do these pieces grow if you add the bifurcate horizon? Is it like as you
Can you say it again? So if I take this point to the bifurcate horizon?
yeah, so as is like terms they're competing when you go close to the bifurcated horizon is something like the electron contribution and bulk contribution changing with different.
If I approach the bifurcated horizon, this entropy will actually be equal to this entropy. Just this bulk term here will be equal to this bulk term here. But then this has extra contributions. So this contribution will never be minimal in that case. So it's never going to be relevant. Yeah. Okay. So I'm not going to actually do the calculation of looking for the quantum extremal surface for the disconnected surface, but I'm going to tell you what it looks like. So you find
For the electron, you are still going to take the classical solution.
the eternal black hole dilaton,
Like a classical solution. Goes up here, etc.
etc. Exactly. So the erase this. Okay, so I claim that you find a family of quantum extremal surfaces that approach the following locus of points. Look something like this. All the way down, but I'm just going to stop there. And by this I mean, for this time, it's like a point there. For this time, it's like a point there. And for like a time in the future, it's a point there. And so on and so forth, okay? So the quantum extremal surface for the state at this time is these 2 points. For this time, it's these 2 points. For this time, it's these 2 points, and so on and so forth. It follows a locus of points like that. I claim also, well now, the issue with this computation is that it depends on the details of the matter CFT that you're considering, because that's the entropy of the union of 2 subregions, right? So it has a non-trivial cross ratio, and so it depends on all the data of your theory. But I claim that what actually happens here is that as these points go up, there's an OPE limit. You're approaching some sort of OPE limit where this point and this point are very close to one another. And I claim that in that limit, I forget if the cross ratio goes to 1 or 0, S bulk of sigma L XL union sigma R XR is simply equal to S bulk of sigma L XL plus S bulk of sigma R XR. Okay? So this is what happens in quantum in QFT when you compute entropy. If you have these 4 points and you take these 2 points together, there's an OPE limit where now you just consider the identity sort of contribution, and then you get that. Okay? This is just a statement that the 4-point function of the twist fields can be well approximated in this limit as the product of the 2 point functions. That's what I'm saying. But now there's something interesting that happens in this limit. The left and right extremizations decouple. Right? So it was phi L plus phi R plus something that depended on L and R together. But now it's L by itself, as in phi L plus SL, and phi R plus SR. No.
Right near the end.
Mm-hmm.
Not everywhere.
Mm-hmm. Yes, Subat?
So this one thing is funny because this to be GT theory coupled to conformal matter. This is something we believe does have a holographic rule, like just by itself without having these additional triangles added up.
Not necessarily.
I'm worried about the fact that about the definition of that in particular, if you didn't have these triangles and you just thought of some region scale boundary, do they have information about the particle or not?
I mean, that region contains the boundary, so yes, you have only information about the bulk.
So I mean, so you have the same issues about the lack of factorization in the bulk.
No, so that's the thing. So this formula is to be applied in the semi-classical approximation. So in some sense, the algebra of observables that I'm considering in these regions are not the entire algebra, so they don't really know about the entire bulk.
Somehow, because at some point when you have it's somehow that there's some error being made that you're post-screening this S bulk entropy. So this S bulk is somehow it's a post-screen, right? Because you included this, because you looked at only setting point functions and then you define the entropy with respect to that. So it's like a free field approximation.
I don't want to say it's a free-field approximation. I want to say it's a semi-classical approximation. Because as in the CFT here did not have to be a free CFT. That's all I meant.
Yeah, the CFT, but you turned off GD.
Correct. As in, it's some QFT living on a fixed background. That's the approximation I'm making. I agree that it seems like it's a bit too coarse, but it's surprising that it's going to give us the results that I'm trying to get to. Yeah. Okay. Okay, so it's a separate extremization for the left and for the right. But this spacetime has a boost symmetry. So it has a boost symmetry. So if I find a quantum extremal surface here, because of the boost symmetry, the answer that I get here is going to be the same for all time. Because I can just boost. There's a killing symmetry in this spacetime. And therefore, the disconnected answer at late times is a constant. Okay, that's the point. And not only that, so SLR disconnected. I claim, so I drew it sort of close to the horizon on purpose. It's actually very close to the horizon. It's in terms of sort of a Schwarzschild radial coordinate. It's like almost, I guess, an L Planck distance away. And so this disconnected surface is really, it's approximately just the dilaton, or twice the dilaton at the horizon divided by 4G Newton, plus S bulk terms. S bulk terms, which are small. These are roughly the central charge times log of the central charge times G Newton, the two-dimensional G Newton. You get something like this. So this is small, so it is small compared to this term. The matter C is small compared to 1 over G Newton. Okay? But the point here is that we have this term, which is simply twice of the Bekenstein-Hawking entropy. That's what we expected for this coarse graining. I wrote SBH here. I was thinking of it as SBH of 2 horizons. You can put 2 here if you like. But it gives us a constant. So it gives us this thing. So now we have 2 possible contributions to the quantum to the entropy of LR. There is the contribution from the trivial surface, which is the thing that just grows linearly in time. And we have the contribution from the disconnected surface, which for the most part, let me ignore the intermediate times, is a constant. Okay? And now applying the minimality condition tells you that the entropy is the smaller of the 2. Lo and behold, we get the page curve. Okay? So this is how we get the page curve for the black hole, the left-right system.
So what's the time at which this transition happens?
Page time.
But there's a boost symmetry, as you said.
No, there's a boost symmetry in that this contribution is constant. That's what the boost symmetry gives you.
Yes.
But the trivial surface contribution starts small and it grows as a function of time. It's not a constant. Remember, we're evolving both sides together like this. Okay? Good.
Look at the time is minus 8. So the time where
Oh, here, yes.
At that time in the past is minus infinity or?
Yes, minus
Is
infinity.
minus infinity.
Yes.
So,
I'm starting at t equals 0.
but what happens if you go into the past?
Same thing, symmetric.
Past, it rises again and then
Yes.
becomes a constant?
Yes.
What's the statement that the entropy was down?
Yes, and then went up. Yes.
No, this is the
I mean, since it relies on this minimization principle, so what is, I mean, this is a proposal, or I mean, what is the status of?
I'll derive it. I'll talk about that later.
the fact that it goes up in the past and then it becomes the this is
You mean goes down and then goes up?
it goes up.
Yeah, right. The entropy starts constant,
Yes.
goes down at t equals 0 because now you have this special state, the thermofield double. Then it goes up and goes to constant again.
And this has to do with the fact that your state had some phases, like you could have changed the phases of the state. You could have a different initial state, so it could have gone down at a different time.
Yeah. It depends on the relative time between the two sides.
So if I think of the original LR system, I have this LR coupled to this bar. So I could think of it as say one CFT and some quantum dot.
Mm-hmm.
Then the statement is you look at our system, and the LR system has this curve. Right? So it has so at some point it kind of spontaneously disentangles from the.
Mm-hmm.
So
Well, not spontaneously. I mean, kind of gradually, but yeah.
Yeah. So so you started off with a system where these things were maximally entangled, like the quantum dot and this thing.
Yeah.
And then you waited for some time, and at some point they just started. There was a fluctuation. They started disentangling.
Yeah. I mean, it's
the second law.
yeah, exactly. That's right. That's like saying I start with a bunch of particles in my hand here, gas particles, and then they all travel around in the room. Now let me time evolve backwards. They all come back here, and then they go through each other and they become typical looking again. That's what the thermofield double is, right?
So it's spontaneously disentangles and then reentangles.
Yes. Exactly. Okay. So what did we? So okay. Is there a question?
Value of the dilaton at the horizon. Sorry.
What's the value of the dilaton at the horizon?
Is it, what is it?
It's some order 1 number. Well,
It's not 0.
no, it's not 0. No, the dilaton is like the area. It gives you the entropy of the black hole. It depends on the temperature. It's linear in the temperature, if that's what you want. So let me briefly recap what we saw so far. So we computed the entropy of the black hole, and we got the correct anticipated answer, which is we found the page curve. And we computed the entropy of the radiation, and we did not get the correct answer, right? The radiation is this ever-growing line. And the idea is that up to this point, in computing the entropy of the radiation, we did the exact same calculation that Hawking did. Okay, and we got the same answer. So there's no problem. There's no paradox there. So it's more of a consistency check, really. But we want to know how will the entropy of the radiation be fixed. In computing the entropy of the black hole, we sort of got a hint, right? So at early times, it agreed with the answer of Hawking, but then it switched to this different answer. It's this application of the RT formula, or this Engelhardt-Wall generalized entropy formula, that gave us a different answer, and we want to be able to apply something like that for computing the entropy of the bath. That seems to be what's missing. And the thing I'm going to consider soon is a context in which it makes sense to apply that RT formula for the bath. But for now, before doing that, let me sort of analyze this case, and by that I mean I'm going to assume this relation and see what it tells us the answer for the bath should be. Okay?
This comes from unitarity.
From unitarity. I'm going to assume unitarity and see what pictures I get. So in computing the entropy of LR, we found the following thing, that at early times, the correct surface is the trivial surface. It did something like that. At late times, we got a surface here, near the black hole horizon. This actually tells you that when you compute the entropy of the bath, the answer at early times should be given by the semi-classical answer, like that. But at late times, you need to include a contribution coming from a region in the bulk. So these 2 points connect to these 2 points, which I will call this region I. And the correct answer for BLBR can be written as follows. It's the von Neumann entropy, the bulk von Neumann entropy. No, let me write von Neumann entropy. Confusing. Of the union of BL, BR, and this region I, plus the dilaton evaluated on the boundary of I. This is equal to, I'm talking now at late times, so late times. This is equal to the entropy of LR, which we said is equal to the von Neumann entropy of this region and this region, which I guess let me see, I need to call them something. I guess I called them sigma before. Let me say that. The union sigma L, sigma R, plus phi on the boundary of I. Right? First, let me make sure that you guys understand this formula here. This is what we just saw. Right? So the entropy was the sum of the 2 dilatons, phi L and phi R. That's the entropy of the boundary of I, plus the von Neumann entropy of union this region plus that region. Okay? You can look at sometimes you can look at the complement of the complement of this calculation, which is this. The entropy of these, the bulk entropy, or just the entropy of the quantum fields of this region union this region, is equal to the entropy of its complement on this Cauchy slice. And that's why it's equal to the entropy of this union this region, union that region. That's what I wrote down here. And the dilaton term is the same on both sides. Okay? So it tells you that at late times, that you're somehow supposed to allow for contributions in the bulk of these disconnected regions, which we call islands. So the prescription somehow is, yeah, maybe I should just stop there. Let me see.
Have an independent proof of this.
Exactly. And I will do so. But let me first make a statement about why this is, has the right structure for what we want. Right? We had these Hawking modes.
This I is universal.
Yes. The
Universal is connecting these 2 points.
not I is the I is a, no, sorry. You're supposed to think of extremizing the locations of the boundary of I. Yes, exactly. You're supposed to extremize this functional, where you extremize the location of I, or the boundary of I. So you're extremizing the union of this entropy and the area coming from the boundaries. Okay? That's what we deduce from this from the unitarity requirement. When you're computing the entropy, like when you're computing the entropy of a quantum system entangled with a gravitational system, you're supposed to allow for possible islands in the gravitational system, which are located via this extremization procedure.
I mean, what is worrying me about is the issue of rigor and proof.
Of what, sorry?
Rigor and proof, actually.
Yeah, I'll prove it. Relax. First, let me just sort of motivate this formula a bit more. So why does this result in the entropy of the bath decreasing, or said differently, not growing as fast as you might have thought? Well, let's think of the process that led to the increasing entropy. So we have these Hawking modes. You know, this is one partner is here, the other partner is behind the black hole horizon. That's why the entropy went up. But oh snap, that other mode is contained in I. And that's why the entropy doesn't grow. So this process, which otherwise would make the entropy grow, in this case, doesn't do anything. And that's why the entropy stays constant.
Just, I mean, this is a question asked earlier. If you just think about the boundary perspective, isn't it kind of clear that SLR will have the same, you know, will have this kind of curve? Just think of the boundary perspective and just think of ER. But the earlier picture where you replaced the middle with L.
But is that the same thing as assuming unitarity?
No, I just have a complete quantum mechanical system, yes, and I entangle them and I prepare displacers. Actually, it's pretty good to an honest boundary calculation.
Yep. Yep. If you start with a unitary system, you'll get the expected answer. But here we're trying to reconcile that with our understanding of bulk physics. And it seems like the thing that fixes the calculation in the bulk is something like this. You include these islands and they fix the answer for you. And now I'm going to give an example where this thing comes out manifestly, and then give a more general proof.
More about how this transition happens, like when you go from one starting point to another. Like how does it do geometry? Like when this I appears at page time.
Yes. So far, how it happens geometrically is, literally, at some point, you have these two possible surfaces. And so far, I only give you a prescription, which says that you're supposed to take the one with minimal generalized entropy.
So both exist.
They both exist.
At all times.
Yeah. But I'm going to tell you more later about how non-perturbative physics gives you this prescription.
At some point in time, around page time, the starting point shifts.
Yeah.
On this calculation, it shifts from this trivial surface.
Precisely.
And you're saying at the same instant, I should also think of this calculation. Think of this calculation. Of the I as the dominant. The islands is.
Yeah. Ultimately, I'm going to talk about a calculation of the entropy of the bath via using the replica trick, and I'm going to review sort of computing the Renyi entropies, and there are various saddles that contribute to this calculation. One of them gives you the trivial surface, and the other one gives you this disconnected surface. And these two saddles, at least in some limit, are weighed by the generalized entropy. And so when working at large n, this imposes the minimality constraints. But I'll get to that later. This is just a small preview.
Was the fact that you had a horizon importantly, because you're in the GD case, that's the eternal black hole. Let's say you found some high dimensional situation. Was the fact that you had a horizon here important at all? I suspect that there might be examples where this thing happens, and where I require islands but don't have horizons, but I have yet to find them. But I suspect. The following example where I would suspect something will happen. High-dimensional system, and let's take the state, but let's put it at a temperature that's below the Hawking phase transition temperature.
Yeah.
So you have these systems, and at some point, and they're just this coupled tube is connected to has some gravitons. So you have exactly the same curve because there's a point where you have entanglement and then entangle with each other and then they disentangle. So you expect, and so you should be able to get the. So the fact that you had a horizon here somehow doesn't seem to be important. You'll get the page curve there as well. I mean, you'll have a page curve.
Okay, maybe we should talk about this more, but there is an example that I know of actually, which in some sense, I mean, it's still in 2 dimensions. It's the case where we don't have a horizon. It's the case where we have a bath at 0 temperature coupled to an extremal black hole, which is also at 0 temperature. So the horizon that you have is the Poincaré horizon. And even there, the island is relevant. So maybe that's the best example that I have for you.
I was actually just trying to understand whether this had to do with this essentially black holes, because there is a boundary page curve. So you take the boundary and you expect page curve.
Yeah.
So I think of this as a holographic derivation of the boundary page curve.
No, but you see this formula?
Because I think it should work even if you think for this gas example, in case you didn't have black holes.
Yeah, the only issue I'm worried about is that the entropies there are not, they don't grow as n. So I won't really have very sharp. Yeah.
What happens? There's an order 1 entropy.
Yeah. So it won't be as sharp as this. That's my worry, but I think we should talk about that later.
You'll get a curve. It won't be an n, but you'll get some smaller curve.
But that might not be as sharp as this curve. Yeah. Okay. Let me see. So the thing I was going to talk about next is an example and then the proof. We said we wanted to stop at 11:30, right? Yeah, I think it's actually good to stop right now for 5 minutes. Okay? Yes.